This is 2019 USAMO problem number 5. The same problem also appeared as the JMO problem number 6, and here is a view of this problem. Two rational numbers, m over n and n over m, they are written on a blackboard where m and n are relatively prime positive integers. And at any point, Evan may pick two of the numbers, x and y, written on the board at that time, and write either their arithmetic mean or their harmonic mean on the board as well. So you add, so you keep extending your set. So you start with a set which consists of two numbers, m over n and n over m. Obviously one of them will be, because they are relatively prime, one of them will be less than 1, the other one would be greater than 1. And then as you take the arithmetic mean, or their harmonic mean, I would say, you would see if it's ever possible to reach to 1 in finitely many steps. So if you draw the real line, this is the number 1. So you have m over n, something like this, and then n over m. And you keep taking averages. So for instance, if you start with these two, suppose that after we take the first arithmetic mean, for example, we would get 1/2 of m over n plus n over m, which is midway through between the two, right? So somewhere here. So what you do is now you include this point as well. And now you keep continuing the process. You keep ever expanding this set, taking arithmetic mean and harmonic means to see if to see what restrictions for what pairs of mn starting points it is ever possible to reach the point 1 in a finitely number of steps. So when you start working on a problem like this, you should have obviously paper, pencil ready and start working on a lot of examples until you feel confident of what's going on and eventually come up with the pattern ultimately. Anyhow, so back to this problem. So let me go ahead and work out with numeric. You can either work out, like, you can keep the m and n if you wish, or you can directly replace m and n with actual numbers, and I did so as well. So for instance, I was thinking of using 2/3 and 3/2, and let's see if I start with these two numbers, what other numbers can be included into our set. And one more thing, obviously arithmetic mean is significantly easier to compute compared to harmonic mean. To be honest, I almost never use this thing. Most of the time I prefer to use this one actually, m over n. Oh, well, in this case, if if you use x and y, in that case it would be 2 over 1 over x plus 1 over y, right? So the 2 over the sum of the reciprocals of these two numbers. But anyhow, so my main idea right now is the following. Let me try to expand this set here using only arithmetic mean and see if how far I can go with that, or if I can ever reach to 1 by just using arithmetic means. And then I will also include the harmonic mean into the picture as well. All right, so let's start with these two elements and let's add their arithmetic mean, so which is 1/2 times 2 over 3 plus 3 over 2. And actually I'll just leave it like this. Well, after a few, again, trial and errors, you realize that it is much more manageable algebraically to leave the expressions in terms of the originals. All right, so let's add another number into our list. For instance, I can this time pick this. Each time in this process, I pick two numbers. So right now in my set, I have 3 numbers. Let's pick this time. Let's pick this number and this number. So let me do it elsewhere here. So 1/2 of 2/3 plus 1/2 of 1/2 2/3 plus 3/2. I guess it's clear. Then that would be equal to, well, again, because I want to express everything in terms of 2/3, 2/3, and 3/2. So what I can do is I can factor out 1 over 4. So in terms of 2/3, I have 1 over 4 2/3 here, so 1 2/3, and then we have 2 more 2/3, so that's 3 2/3 plus, and then the 3/2 is only 1. And make sure you understand the algebra actually. Okay, so I can basically include this number into my list now. 1 over 4, 3 times 2/3 plus 1 times 3/2. All right, let's add another number here. So this time, for instance, I can, why not? I can use this thing which I just created and this thing to, so let's see again. So I have 1/2 times this number, 1/2 2/3 plus 3/2, plus 1/2 times this monster, 1 over 4. 3 times 2/3 plus 1 times 3/2. All right, so again, I can factor out. So there's a 1 over 16 here. There's a 1 over 4. So we can factor, oh, sorry, 1 over 8 here. So we can factor out 1 over 8. So again, let's try to keep track of the coefficient of 2 over 3 here. So we have 3 here after we factor out 1 over 8. And then this one I need to multiply by 2 further. So this is 1 over 4. So this is 2 over 8. So there's a 2 coming from this one. Oh, sorry, 2 plus and then 3 from this side. So 5, right? So this is 5 times 2 over 3 plus, how about 3/2? We have 1 coming from this, 1 times 1. And then 3/2 on this side, it is 2 more. So it is 3 times, I think. 3 over 2. Okay, we can also add this thing to our list, and obviously so far we have not reached the number 1. You can easily realize that this number is not 1, and obviously this one is not, well, after you play with the numbers you see that they are not equal to 1. So we have 5 times 2 over 3 plus 3 times 3 over 2. All right. Let me do one more, but by now you can see what's going on, right? So in particular, so each time we have 1 over a power of 2. That's nice. And then look at these coefficients, right? So it's obviously they add up to a power of, well, they add up to 4 exactly here. And these two, 5 plus 3 is 8 exactly. And in fact, you can reinterpret this as 1 here and invisible 1 here as well. Let's do it one more time just to make sure that everyone sees that. So for instance, this time I will start with this newly generated number here, and I will add, let's say, 1/2 of this or one of the original numbers. So we have 1/2 times 1 over 8 times 5 times 2/3 plus 3 times 3/2. Yes, plus 1/2 times, for example, we suggested to use this one, 2 over 3. So that whole thing is equal. So we have 1 over 16 here. Okay, so let's have a look at the coefficient. So 1 over 16 will be out there. So 2/3. There's a 5 here. 2/3. That's 8 over 16. So 5 plus 8 is 13 times 2/3 plus, and well, obviously we can already make a guess. So because they always add up to the denominator, so this is probably going to be a 3 here, right? And is that so? Well, it is obviously 3 times 3/3 because there's no other coming from this one. 3 times 3 over 2. Awesome. So well, I messed up pretty badly here. Like I have a lot of, I mean, it's not messed up, but it is kind of dirty. Okay, so yeah, there you go. Let's add this number into our list as well. 1 over 16, 13 times 2/3. Again, 3 times 3 over 2. In fact, it would have been a really good idea if I tracked along the line, if like, because our goal is to reach to the number 1, if we are actually approaching 1 properly, right? But I'll leave it to you to notice that, to see that none of these numbers are yet equal to 1. Okay, so but under what conditions such a thing could be equal to 1? And one idea, like when you think about it, the simplest possible case, well, a few observations. One of the observations is, by now you guys realize that it is totally like we can quickly make an abstraction here, right? We can easily replace 2/3 and 3/2 with a over b and b over a, obviously, or m over n and n over m, I should say. And so think it in a more abstract level, right? So let me first write that down. So basically what I'm saying is we would have, so far I'm only using the arithmetic mean. I haven't started with the harmonic mean yet. But so the main idea is each time we obtain a new number would look like it's a power of 1 over 2k, and then we have our two original fractions, let's say a over b and b over a, and then they have coefficients in front of them, let's say u and v, where u plus v is equal to 2 to the k, this number. Do you guys see that? So one kind of idea at this stage is kind of using some wishful thinking. How in the world can I make this whole thing equal to 1, right? So that's the main goal of the problem. And I think one idea that stands out immediately is that if I can have this u and v exactly match with that b and a, then I would be done, right? So because if indeed, so wishful thinking, whatever you call it, if u was equal to, so this is just wishful thinking, b and v is equal to a, then because these things will cancel out, u and b, so we will be left with a here, and then v and a will cancel out, and we will be left with b. Then the whole thing is equal to, so this expression turns out to be equal to 1 over 2 to the k times a plus b. But wait, we just said that a plus b is equal to u plus v, right? 1 over 2 to the k times u plus v. But u plus v is just 2 to the k. Aha! 1 over 2 to the k times 2 to the k, and that's simply equal to 1. So that's automatically gives us a very nice solution. And can we do it? Yeah, of course. Let's try to build one for ourselves. Okay, so check this out. So let's say that our number is, say, 16, for instance. So I have how can I reach 16? For instance, let's have a look at different cases. For instance, we can have 7 plus 9, or we can write it as 5 plus 11, or 3 plus 13, or equals 1 plus 15. All right, so if our goal is suppose to reach, let's say you start with two numbers, let's say 7 over 9 and 9 over 7, and let's say that starting with these two numbers, our goal is to reach 1 using only arithmetic averages, and I claim that this is possible. Simply utilizing the trick that the tricks that we just worked out a few minutes ago. So basically the idea is I will do this thing maybe 4 times, the algorithm, and eventually we will reach out to 1 over 16. And what I really want is I want to multiply 7 over 9 by as 9, and then this one by a 7, 9 over 7, and then this way that those two will cancel, and we would get 1 over 16 times 7 plus 9, and that will give me a 1. So how in the world am I going to get these numbers, the 9 and the 7? And then I can easily show that it's possible for any of the odd compounds, because obviously if m over n, the m plus n, because they are relatively prime, they have to be both odd if you want it to be a power of 2, right? So how can I reach to a 9 and how can I reach to a 7? Remember earlier when we looked at how we built up our thing, we always start at 1, 1. And then eventually, depending on what you add, for instance, here in the first step, when we added 2/3 only, and mixing it with the previous guy, this guy, it turns out that we were able to reach to 3 and 1. So we didn't add any to this, and all we did is to increase the weight of 2/3. So it's kind of, we are creating those weighted averages in a sense. Does that make sense? And for instance, in the next step, what I tried was, well, this step was a little bit more complicated, but have a look at these simple cases. When you start with something like this, a 5 and a 3, and in the next step, you mix it with 2/3, so just this thing. So when we add, so basically we are adding an 8 to this guy and nothing to this guy, and boom. So that's exactly what, so basically, long story short, what I can do is I can make it look like this. So 9, I need a 9 here and I need a 7 here. So for the 9, starting with a 1, and because I need to add up all the numbers from, I will be adding a 2, a 4, and an 8, right? So, okay, I'll show you the details in just a minute. So in order to reach the 9, all I need is add an 8 here, times 7 over 9 plus, and then for this one, because I need the 7, I will add the 2 and the 4. Okay, so this kind of gives me the steps in the procedure. So here I start. So we go, so first we are, in order to reach 1 and 1 first, we need to mix the 2 first. Let's mix the 2. So we have 1/2 times 7 over 9 plus 9 over 7. So we are done. Or maybe I should have written it. Okay, so let's write it like this. 1/2, 1 times 7 over 9 plus 1 times 9 over 7. Okay, in the next step, I'm going to mix the average that we got so far, this number, and okay, so because I want the 2 and the 4 to go to 9 over 7, I will mix them with 9 over 7. And then 2 times I will mix it with 9 over 7, and eventually I will mix it with 7 over 9. Okay, so let's do it. So I have 1/2 times this monster, 1/2, 1 times 7 over 9 plus 1 times 9 over 7 plus 1/2, again, I said 9 over 7, right? So 9 over 7. Okay, let's mix those two. So 7 over 9, its coefficient won't change, so 1 over 4. So 1 times 7 over 9 plus, so this has 2 over 4, and then there's another 1 over 4, 9 over 7. So 2 over 4 plus 1 over 4, it's 1 plus 2, right? So do you guys see that? 1 plus 2, which is a 3, times 9 over 7. I think that's clear. And then I keep doing the same thing. So again, I want the 4 next to it. So here, so therefore I will use 9 over 7 again. So we start with this guy. So 1/2, 1 over 4, 1 times 7 over 9 plus, well, this is 3 times, right? 3 times 9 over 7. Or maybe we can just leave it like it is. 1 plus 2. Plus, am I missing a bracket here? Yeah. 1/2. Again, we need the 4 to be with, okay, so I need a 9 over 7 again, because that's equal to, so this is a 1 over 8 now. I have 1 over 8 factored out. So the coefficient of 7 over 9 won't change, because, so we keep mixing it with 9 over 7, if you will. And then you can easily confirm that this is 1 over 8, 3 times 1 over 8, or 1 plus 2, and then 1 over 8 is factored. So there's a 1 plus 2 here. And from this one, we will get also a 4 over 8. 1 plus 2 plus 4. 1 plus 2 plus 4 times 9 over 7. And finally, now it's time to mix with 7 over 9. Okay, so let's do it yet one more time. 1 over 8 times 1 times 7 over 9 plus... okay, so these numbers, okay, are messy. 9 over 7 plus 1/2. We decided to mix it with 7 over 9 this time. So that's 1 over 16. We can factor out the 1 over 16. There's a 1 over, there's 1 7 over 9 here. And then when you do 1 over 16, this is 8 over 16. So there's 8 more. So 1 plus 8, 7 over 9 plus, and then the other one didn't change. 1 plus 2 plus 4, 9 over 7. Aha! And that's exactly the number I wanted to reach, right? So that whole thing is equal to 1 over 16 times 9 times 7 over 9 plus 7 times 9 over 7. And the 9's cancel, the 7's cancel. We have 1 over 16, 7 plus 9. And that's just 16 over 16, and that's just a 1. In a similar way, for instance, how would you obtain, let me just give you, so how can you obtain, for instance, you starting with 5 over 11 and 11 over 5, how can we obtain a 1, right? So again, we think, okay, so 5 over, okay, so we start with 5 over 11 and 11 over 5, and we want to reach to a 1. So basically I need to multiply this one by 11, this one by 5, and this one would be 1 over 16. So in order for, and this is obviously 1, so in order to get to 11 and 5, I think the idea is clear. So this one will be 1 plus 1 plus, I probably need a 4 here, right? And then for this one I will use the rest. That's it. And these numbers obviously add up to 16. It's just perfect. So basically, how should I mix it? So basically, I will start by mixing the first two, so 5 over 11 and 11 over 5. First, I will mix these two, and then I'll get a mixture. And then using this mixture and which one? I want the 2 to go to 5 over 11, the mixture and 5 over 11 again, right? So mixture and 5 over 11. Okay, let's use the left side for that. Mixture and 5 over 11 will give me a new mixture. And then I will need 11 over 5 this time. So mixture and 11 over 5 will give me yet a new mixture. And then finally 5 over 11 again. The resulting mixture and 5 over 11 will give me the remaining mixture. And I should, so basically, okay, so long story short, okay, so we have at least a claim without even resorting to the harmonic mean, just using arithmetic mean. If two numbers m over n and n over m are such that m and n are relatively prime and m plus n adds up to a power of 2, then I can, just using arithmetic mean, I can obtain 1. Does that make sense? I can reach to the average of these two numbers, make it such that it is equal to 1. Now, how does things change when you have harmonic mean? And in general, it turns out that there is no other way to do better. And so, well, okay, so what I mean is, there's no other m and n values besides the fact that besides the m plus n being a power of 2, you can never reach to 1 even when you use harmonic mean. Okay, so let's prove it, right? So far what we did is, our claim was that if you start with m over n and n over m, so where m and n are relatively prime, and m plus n, oops, that's m%, is 2 to the power k, then yes, right? So then using arithmetic mean, right, means we can reach 1. And now I further have a claim, there is no other way. There is no other way to reach 1, even when using harmonic means. Okay, so and it turns out that this part is very easy. The hard part of the question was this one, so the observation we did earlier. This part is quite simple. In fact, you can easily use modular arithmetic to figure that out. So for instance, if let's assume to the contrary, that, or you don't even need that basically. So that, but okay, so let's just use this notation, I guess. M plus n is equal to 2 to the power something times an odd number. So basically it has an odd divisor, i.e. there exists a p, odd p, there exists an odd p, there exists an odd prime p which divides m plus n. Well, that means, so therefore, so m plus n is congruent to 0 mod p, or if you will, oops, let's go back. Hold on. Yeah, if you will, further that would imply that m is congruent to minus n mod p. Now let's abuse the notation a little bit, but I think it's clear. Therefore, if you divide both sides by n, for instance, m over n is congruent to minus 1, and if you divide both sides by m, you would realize also that minus 1 is equal to n over m as well. So both of these guys are congruent to minus 1, n over m. They are both congruent to minus 1 mod p. And it turns out that this is like an invariant. So what happens is, in mod p, all of these, like not only the starting points, the starting rational numbers, but all the rational numbers that we can obtain by combining these two, either using arithmetic mean or doesn't matter, harmonic mean, will always give you a negative 1. For example, let's quickly check. So if you check the arithmetic mean first of these two numbers, any two numbers, m over n plus n over m divided by 2, but that's just congruent to minus 1. So this guy is minus 1, but the other one is also minus 1. All divided by 2, so minus 2 over 2, and that's just minus 1 mod p. But wait a second, our goal is to reach 1 mod p. And obviously for an odd prime p, 1 is not congruent to minus 1, right? And well, so these two, 1 and minus 1, are only congruent to each other if the mod is 2. And okay, how about the harmonic mean? So you 2 over the reciprocals, so 1 over m over n plus 1 over n over m, which is just 2 over m over n plus n over m. The same thing, minus 1 plus minus 1. This is just 2 over minus 2, which is again congruent to minus 1 mod p. But we want to reach to the point 1. Do you guys see that? So again, there's no way. Minus 1 is definitely not congruent to 1 mod p, where p is odd. So that gives us the desired contradiction that it's not possible to, well, this is not even a proof by contradiction. I mean, so assume to the contrary that m plus n is equal to 2 to the k times an odd number, and we can reach to 1. No, we cannot reach to 1. You repeatedly keep applying this procedure. Every new number that you create will still be congruent to minus 1 mod p, and you take whatever combination, this process will never end. So this is a contradiction. So therefore, no such thing. So for any time that you have m plus n, a prime factorization like this, not gonna work. And that's it. So hopefully this helps, and I think it was kind of okay. So yeah, once you realize the main trick, which turns out to be not that bad after all, yeah, so, but overall a very neat problem, very nice problem. Hope you enjoyed it, and looking forward to see you guys in our next lecture.